Let's do some problems. Okay, on groups and group actions and so on. So here's problem 1. So to state this problem, let me first recall something about symmetric groups and cycle decomposition and so on. So recall, if I take the group G to be the symmetric group Sn, so n is, let's say, at least 2 symmetric group, and if I take a typical element of Sn, I have a cycle decomposition, right? So sigma has a cycle decomposition. Recall, this means that you can write it as a product of disjoint cycles. So let's maybe do it by example. Suppose n is 9, so I'm looking at S9, and if sigma, say, is the element, it's a product of 1, 2, 3, 5, 6, 9, 4, 7, 8. Okay, so this is a permutation of the numbers 1 through 9, and this cycle decomposition just says that, for example, that 4, 7 and 8 form a 3 cycle. In other words, sigma maps 4 to 7. So this is what sigma does. It maps 7 to 8 and it maps 8 back to 4. Okay, so the element 1 is mapped back to itself and so on. Okay, so there are some 2 cycles as well. 3 goes to 5, 5 goes to 3. So recall, this is what decomposing a permutation into cycles means. Now here's what I want to look at. I want to sort of study the lengths of the cycles, or maybe for a start, let's look at how many 1 cycles does do the various elements of Sn have. Okay, so what do I mean by a 1 cycle? So here, for example, this particular example of sigma, this particular sigma has 2 1 cycles. Okay, so it actually has 2 1 cycles. Okay, by 1 cycle I mean the length of the cycle is 1. In other words, this 1 is really a fixed point of sigma. Sigma maps 1 back to itself. Okay, it actually has two cycles as well. So this has two cycles, okay, which are 3, 5 and 6, 9. And it has 1 3 cycle, which is 4 going to 7 going to 8. Okay, so this is the 3 cycle. There are 2 1 cycles and there are 2 cycles. Okay, so in particular, what's the total number of cycles, if you wish? So total number of cycles is 5 in this case. Okay, so 2 plus 2 plus 1. Okay, so here's the first problem. So this was all by way of preliminaries. So now let me state the problem. So let's consider the following sum. So prove that if you take the sum over all elements of Sn, I take the number of 1 cycles in sigma, this sum will always give me the answer n factorial. Okay, so the sum of the number of 1 cycles of sigma, sum over all elements sigma ranging over Sn, gives me the order of the group Sn, which is n factorial. Okay, so let's check this out in some easy simple cases. So example, suppose I just look at the symmetric group S3, and let me just write out all the elements sigma. So here's sigma. So this is the identity element, 1 going to 2 going to 3. I'm sorry, 1, 2 and 3 each going to itself. Here are the transpositions which only permute 2 of the elements and leave the third one fixed. And there are these 3 cycles. Okay, so there are 6 elements of sigma. Now let's tabulate the number of 1 cycles. Okay, how many 1 cycles do we have in each? So here there are 3 1 cycles. Okay, this guy, the next one, has only 1 cycle, which is just this singleton 3. Okay, likewise, these two also have only 1 cycle. These two permutations, the last two guys, don't have any 1 cycles, because in fact it just has a single 3 cycle. Okay, so let's add all these up. So that's 3 plus 3, which is 6, which is exactly 3 factorial. Okay, so this is an instance of this problem, this example. If you take n equals 3, you do actually get 3 factorial. Okay, so let's see, how does one prove statements like this? Often many of these problems can be rephrased appropriately as a problem about group actions. Okay, so at this point I would encourage you to sort of spend some time trying to work out the solution on your own, but let me also tell you how to do this. So if you don't succeed, here's the solution, which you can look at maybe for hints or for the entire solution. So here's the idea. So let's take this group Sn and let's look at a following natural set on which it acts. Okay, so this is the set of all numbers from 1 to n. Okay, so recall this group G acts on this set X in the following natural way. If I take an element sigma in Sn, how does it act on element k from this set X? Well, k, since it is some element from 1 to n, and sigma being a permutation of the numbers 1 to n, sigma will act on k and give me some other number between 1 and n, right? So here's the definition. You just define, so the definition, I define sigma acting on k to just be sigma of k. Okay, so this is the definition. Okay, and of course that's also an element of X. Okay, and it's easy to check this is an action. So this is an action, sometimes called the defining action of this group Sn. In some sense, the group it occurs naturally as the set of all possible permutations of the set. Okay, now let's do the following. Let's look at this orbit counting statement. Okay, so we have the theorem which tells us how to determine the number of orbits for an action of a group. So let's study the orbits first. So let's first ask ourselves, what do the orbits of this action look like? Okay, if you just spend a couple of minutes, you will realize that in fact there is only one single orbit here. Okay, so recall this is the set X. So what does the orbit mean? Okay, how do I construct orbits? For example, I take one single element of X, say the element 1, and the orbit of this element 1 will just mean I have to act every possible group element on 1 and collect together all the answers that I get. Okay, so on 1 I act by various elements. So I act by some group element sigma, by some other group element tau, and so on. So I keep acting on 1 by every possible group element, and I will get some elements of my set. The collection of all these elements is what's called the orbit of my point 1. Okay, so let's write that down. The orbit of the element 1 by definition is just sigma acting on 1 for all sigma ranging over Sn. Okay, but notice you can always find a permutation which takes the number 1 to any other number between 1 and n. Okay, so by suitably constructing sigmas, I can get every element k here. So this will give me every number k between 1 and n. Okay, in other words, this is just the whole set X itself. Okay, and what's the easiest sigma which maps 1 to k? So if I want an element sigma which takes 1 and maps it to k, well, I can take just the transposition 1k. So I can take, for example, the element 1k, and leaving all the others fixed. So this is just the transposition which maps 1 to k and leaves all the other numbers fixed. This permutation of course takes the number 1 and maps it to the number k. Okay, so this is an example of one such element. So it's clear that the orbit of 1 is in fact the entire set X here. Okay, so in particular it means that the number of orbits, so the number of orbits for this particular action is just 1. Okay, so such an action is sometimes called a transitive action, in which there is only one orbit. In other words, every element of the set can be mapped to every other element of the set by some action of some group element. Okay, so we have determined the number of orbits to be 1. So now let's apply our orbit counting theorem. So what does the orbit counting theorem say? Orbit. It says that the number of orbits is nothing but 1 by cardinality of the group G, overall sigma ranging over the group G of the fixed point set of sigma. Okay, so this is the number of orbits for the group action G on X. Okay, was given by this. So recall this is also called Burnside's lemma and so on, where X sigma is the fixed point set, meaning it's all those elements of X which are mapped to themselves. So sigma of K is K. Okay, this is all elements of the set which are mapped to themselves by sigma, the fixed element of the group. Okay, now this set, the fixed point set, what does it mean? So if I pick some element sigma in my group G is Sn here, what does the fixed point set mean? Well, observe that, what are the fixed points of a permutation? Well, those are exactly the 1 cycles. So let's go back up, look at this picture of sigma that we had. So observe that if you want a point K which maps to itself under sigma, right? That's what a fixed point means. Sigma K equals K. Then these are the only 2 options. So these are the only 2 fixed points. The numbers 1 and 2 are the only fixed points for this particular sigma. Okay. So observe in this example, X sigma, the fixed points are just the numbers 1 and 2. None of the other numbers can be fixed points. For example, when you see the cycle decomposition, it becomes clear. 4 cannot be a fixed point because sigma maps 4 to the next element in the cycle. Okay, and that element is not itself because the cycle has length at least 2. Same thing here, 3 cannot be a fixed point because sigma takes 3 to whatever the next element of the cycle is. Okay, and so on. So the only way you can get fixed points is if that element occurs as part of a 1 cycle. Okay, so what does that mean? We have proved the following, that in fact the number of fixed points therefore is the same as the number of 1 cycles. Okay, is the number of 1 cycles in the cycle decomposition of sigma. And now we are more or less done, because all we have to do is just look at this statement here. Okay, put everything together. So observe, if I take this statement, let me call this equation star. So now I just look at the following thing. The left hand side was the number of orbits, which we know is 1. The right hand side is, according to what we just said, it's 1 by the cardinality sum over all group elements of the fixed point set, which is just the same as the number of 1 cycles. Okay, and now we are done, because these two things are equal, and that's exactly what we had to prove. Okay, so proved whatever we needed to prove, which is this statement up here, that the number of 1 cycles in sigma summed over all group elements gives me n factorial. Okay, so that's an application of group actions. So let's do one more along the same lines. So here's problem 2. Now this time it's not the number of 1 cycles that we will look at, but rather we will just look at the total number of cycles. Okay, so now I'm going to just say, let me look at the total number of cycles. Total number of cycles in the cycle decomposition of sigma. Okay, so what does that mean? Let's go up again. Here, for instance, the total number of cycles was 5. Okay, so I don't care what the individual lengths of the cycles are. I just want to know how many total number of cycles there are. Okay, so I take the total number of cycles, but I do something slightly different here. I look at 2 raised to the total number of cycles. Okay, 2 to the power of total number of cycles summed over all elements of the group Sn. Now I claim it gives me n plus 1 factorial, not n factorial anymore, but rather n plus 1 factorial. Okay, again an interesting sort of statement. Again, please try this on your own, but here's the solution nevertheless. So as before, in all these things, one should always try this out on some simple examples. So let's do the same example as before, which is the case of S3, and let's write out all the elements sigma as before. I have 1 2 3, 1 2 into 3, 1 3 2. There are 6 elements. Now in each case, let me say how many total number of cycles. So this is the total number of cycles. So here there are 3 of them. Here I have 2 cycles, this one and this one. Here again 2 cycles, 2 cycles. These two have 1 cycle each. Okay, but remember I have to do 2 raised to the total number of cycles, right? So 2 to the number of cycles. Okay, so that's for the first guy it's 2 cubed, second guy it's 2 square, 2 square, 2 power 1, 2 power 1. Okay, so let's add all these numbers up. They're all various powers of 2. So I have 8 plus 4 plus 4 plus 4 is 12, plus 2 plus 2 is 4. So that gives me 24. Okay, and 24 is actually 4 factorial now. It's not 3 factorial anymore, it's n plus 1 factorial. Okay, so that's the next interesting fact about the number of cycles which occur in the various cycle decompositions of elements of the symmetric group. Okay, let's prove this. Again, a proof by group actions. So here's the solution. Okay, so as before, let's look at the group G equals Sn. And it had this defining action. It acted on the set X, which was 1 to n. But we have encountered this following construct. When a group acts on a set, it also acts on all subsets of that set. Okay, so now because I have this action of G on X, it implies I can also consider another action of the group G on the power set of X. Okay, so what is this? The power set of X just means the set of all Y subset of X. Okay, we should say set of all Y, where Y ranges over the subsets of X. Okay, so the power set of X is, well, I also include the empty set here. So we've seen this before. I have a natural action. What's the action? If I take an element sigma from my group G, if I take a subset Y of X, the action of sigma on Y is just defined to be the element wise action. So I take sigma and I act on K for every K coming from the subset Y. Okay, now when I do this, what I generate is again some new subset of X, right? Potentially a different subset of X. Okay, now we had also seen a finer thing here, that this subset sigma Y has the same cardinality as Y. So in fact, you can also say that there is an action of the group G on subsets of X of a certain fixed cardinality also, if you want. Okay, in this case we will not need that finer distinction. We'll just look at the action of G on the entire power set. Okay, but let's make this observation nevertheless. It's an important observation which we will need, that the cardinality of sigma acting on Y is the same as the cardinality of Y. Okay, because when sigma acts on K, for every K in Y, it gives me distinct elements. Okay, so this is an important property. Okay, now again let's do the same analysis as before. Let's understand what the orbits look like for this action and how many orbits there are. So what are the orbits? Well, the first thing to observe is that because the cardinality of sigma y and the cardinality of y are the same, we certainly can't we cannot change the number of elements in a subset by acting by some group element. Okay, so this particular group action preserves the cardinalities of subsets. So let's define those subsets, PD of x. So what is PD of x in this case? This is just all y such that y is a subset of x and y has cardinality d. Okay, so what is d here? D can be 0 and go all the way up to the cardinality of x. The cardinality of x is n in this case. Okay, so in order to understand the orbits, I first construct these elements PD of x. Okay, so these are subsets of a fixed cardinality. Now I claim that the set PD of x is a single g orbit. Okay, so here's the first observation we make, that PD of x, this subset of P of x, forms a single g orbit. Okay, so let's prove this. So what does this forms a single g orbit mean? I have to show that given any two subsets of say cardinality d, I can map one to the other by means of some group element. Okay, or let me sort of do a simpler thing. So let me take the subset 1, 2, 3 till d. Okay, let me call this subset A. So consider the subset 1, 2, 3 till d. Okay, so this is a particular element, particular subset in PD of x, sort of a special guy, the first d consecutive numbers. Now let me take any other subset of cardinality d. So let me write out the elements. Let's call y as, what are the elements of y? They are y1, y2, yd. Okay, this is another subset in PD of x. Some arbitrarily written out elements, I just label them as y1, y2, yd in any way I care. And now let me claim that I can construct. So now observe the following, that I can construct an element in my group Sn that exists sigma in Sn such that when sigma acts on A, I will get the subset y. Okay, and how do I construct this sigma? Well, what is it that I need to do? How do I construct sigma? So I sort of have some, so here's how I construct sigma, b plus 1 to n. Remember, sigma is some permutation of the numbers 1 through n, right? So how do I want it to be? 1, 2, 3 till n. So I need to construct sigma now. So that's what I'm going to. So this map now is going to be sigma. So I already know something that I want sigma to satisfy. Okay, when sigma acts on these d elements, I'm supposed to produce these d elements, right? So there are many different ways of doing it. Here's how I could do it easily. I take sigma which takes 1 and maps it to y1. Okay, so I scan my right hand side, somewhere there is this number y1, right? So I define sigma like this, sigma sends 1 to y1. Okay, I look through my list, somewhere there is y2, sigma maps 2 to y2. Okay, it maps 3 to y3, whatever that may be, and so on. Okay, so the first d numbers I map it to y1, y2, yd in that order. Okay, so define sigma like this, sigma should map I to di, to yi, should map I to yi for I between 1 and d. Okay, and for the remaining numbers from d plus 1 to n, I don't really care. Okay, and just map it arbitrarily so that it's still a permutation. Okay, and define it arbitrarily on j greater than d. Okay, on I greater than d. Okay, when I say arbitrarily, of course the final end product must still be a permutation. Okay, so I have to define it to be some bijection, but all I have to do is y1, y2, yd are already gone, they are taken because they are the images of 1, 2, 3 till d, and so the remaining n minus d numbers which will be there on the right hand side, and then I have these remaining n minus d numbers, d plus 1 to n, I sort of just map these remaining guys to those remaining guys in a one-to-one onto fashion. So some arbitrary bijection of those two sets. Okay, so I hope it's clear that if I take any subset y of cardinality d, I can always find a permutation sigma which will map A to y. Okay. Now, what does this mean? It means that the orbit of A is the entire set PD of x. So, this just tells me that if I take this special set A and I look at its orbit, well, that's everything. Okay. So, PD of x forms a single orbit, and observe that if I take subsets from PD and PD dash of x, subsets of two different cardinalities, then as we have said already, I cannot find a group element which maps one subset here, which maps the subset of cardinality D to a subset of cardinality D dash, where D dash is different from D. Okay. So, what this argument entails is, what it implies therefore is the following conclusion, that the G orbits for the action of this group Sn on the power set of x are precisely the following: P0 of x, this is the empty set, P1 of x, P0x is the singleton comprising the empty set. The P1x is all singletons, P2x and so on till PDX. Okay, PDX is again the singleton comprising just x. Okay, so these are exactly the orbits for the action of this group. In particular, how many? This should be Pn of x. Now, how many orbits do I have? Exactly n plus 1. So, n plus 1 orbits. Okay, now again let's use our orbit counting theorem. So, orbit counting theorem says that the total number of orbits, which in this case is n plus 1, should therefore equal 1 by n factorial, that is the cardinality of the group, times the sum over all sigma in Sn of the cardinality of the fixed point set. Okay, so now this the set on which it's acting is Px, not x. So I need to look at Px sigma. Okay, so I have just applied the orbit counting theorem for the action of the group Sn on the power set of x. Okay, when I do that, this is the equation I deduce from that. Okay, now all that remains is to understand what this right hand side looks like, and I claim that Px sigma, the set of fixed points, the cardinality of the set of fixed points, is exactly 2 power the number of cycles in sigma, the total number of cycles. Okay, so once this claim is established, the problem is done, because as you can see, this sum would then become the sum of 2 to the number of cycles, and I can take this n factorial over to the other side. N factorial into n plus 1 will become n plus 1 factorial. Okay, so if this claim is done, then I am done. Okay, claim implies what we need to prove. Originally. Okay, so the problem is done provided we prove the claim. Okay, so let's try and understand why this is true. So I claim that if I fix a certain sigma with a certain cycle structure, then the number of fixed points for the action of sigma on Px is exactly this number, 2 to the number of cycles. So let's sort of do this by example, maybe for a start. So suppose I take sigma to be the permutation that I wrote out initially, 1, 2, 3, let's see, what was it, 3, 5, 6, 9, 4, 7, 8. So this was a permutation inside S9. So now I'm going to ask, suppose I take x to be the set 1, 2, 3 till 9, then how many subsets of x are fixed under this action of sigma? Okay, so I want to understand px sigma, which is what? Set of all subsets y of x such that sigma acting on y should give me back y. Okay, so let's see what are the possibilities for y. What can be the elements of y? Okay, so let's see. Suppose I take y to have some number, right? Y should have at least one of these. I mean, if y is non-empty, it must contain some number. So let us say for a start, suppose y has the number 4. Okay, let's try to understand. Suppose 4 belongs to the set y. Okay, now what do we conclude from that? So observe, when I act sigma on y, I should get back y. Okay, so if 4 belongs to y, then sigma acting on 4 will belong to sigma acting on y, but sigma acting on y is supposed to be y. Okay, so we conclude that therefore sigma acting on 4, which is sigma evaluated on the number 4, this must also be an element of y. Okay, so what does that mean? Sigma of 4, now remember this is part of this 3 cycle here. So if 4 is there in y, then we conclude that sigma of 4 is also there in y. Okay, so 4, 7, 8. So this is how sigma acts. Okay, so what we have concluded is if 4 is in y, then the next guy in the cycle, which is 7, must also be in y. Okay, now observe, we just repeat the same argument with 7 in place of 4. Okay, so 7 belongs to y, means by the same token sigma acting on 7 will belong to sigma acting on y, sigma acting on y, which is y again. So this implies that sigma 7 is also in y, and sigma 7 is this number 8. So we conclude that 8 must also belong to y. Okay, so what this means is that, so this argument now establishes the following: if one member of a cycle, so 4 in this case, if 4 is in y, that automatically forces the other members of the cycle to also belong to y. Okay, so what that means is that y is therefore a union of some of these cycles. It's a union of some of these cycles of sigma. Not all of them need to appear. So for example, y equals just 4, 7, 8 would certainly be a fixed point. Suppose I take y only to have the numbers 4, 7 and 8, then observe that sigma y is already equal to y. So this is enough. So I can only take those 3 numbers and I will certainly get something that's a fixed point. Okay, or what's another example? I could take a union, meaning here's another example of a fixed point. I can take the elements 4, 7 and 8. Then maybe I can take the element 3 as well, but if I take 3, I am also forced to take its partner in the same cycle. Okay, so I am supposed to also take 5. Only if I do that can I have a chance of y being a fixed point. So in this case, let's see whether this set of 5 elements is in fact fixed. 4, 7, 8. If I apply sigma to those 3, I will just keep cycling through those 3 numbers. 3 and 5, when I apply sigma to 3, I get 5. When I apply to 5, I get 3. Okay, so when I act sigma to this set of 5 elements, I get back the same set of 5 elements. Okay, I get them in a different order maybe when I act on it, but I don't care. I just want the final set to be the same. Okay, so here is another example of a subset of these 9 elements such that sigma acting on x gives me back sigma acting on y gives me back y. Okay, so and so on. So what this means is that in general, how do I produce all these y's which are fixed points? Well, this is just the collection of all unions of some cycles of sigma. Okay, now what does that mean? Well, let's just look at how do we see how many elements there are therefore. Okay, so what do I have? I have the following cycles. So remember, sigma looks like it's got 1, 2, 3, 5, it's got 6 9 and it's got 4 7 8. So how do I find a y? Well, out of these 5 cycles totally, so there are 5 cycles total. So out of these 5, I can choose any subset of the 5. Okay. So I have 5 possibilities. So let me represent each cycle by a dot. There are 5 dots. Okay. There are 5 possible cycles, and out of these 5, I can choose any subset. Okay. For example, I can choose only this last cycle. So then I will get 4 7 8 as my y. If I choose this last cycle and this guy, then the choosing those 2 cycles would amount to choosing the set y to be 4 7 8 and 3 5. Okay, the subset of 5 elements. If I don't choose any of these dots, that's like saying I don't choose any of the cycles. In other words, y is the empty set. Or if I choose all 5 dots, it means I'm choosing all 5 cycles, in other words all 9 numbers. Okay. So it's clear therefore that the possible y's that you can have, the set of fixed points, what's the cardinality? Well, it's just the cardinality of the subsets of these 5 dots, for example. Okay. And how many? Well, that's just the power set of this set of 5 dots, if you wish. Okay. So in our example, so I'm just trying to say what it is in this example. Well, in this example, this is nothing but the same cardinality as the power set of this set of 5 dots. Okay, it's just all possible ways of choosing some sub collections of these 5 dots. But remember, the power set of a set has cardinality 2 power the number of elements in that set. Okay, so in this case, this is 2 power 5. And remember, this 5, where did this come from? Well, it's because there are 5 total cycles. Okay, so in general, therefore, the same argument in general proves the following, that this is just 2 power the total number of cycles in sigma. Okay, and that establishes our claim, and we are done, proves our claim, and thereby the original statement that we wanted to prove. Okay.